the first thing I want to make sure you guys know what to do is how to split up an angle. So let's suppose that you had the angle pi over 12, and you're asked to evaluate the, let's say, sine of pi over 12. Well, this one is not quite as apparent how you're going to use nice angles because pi over 12 is so small. Well, the trick is, instead of using addition, use subtraction. And this is 1. You know you're going to need twelfths. So take two numbers that subtract to be 1, but are going to be nice to break down with 12, to reduce with 12. Okay, so 4 first would work, and 3, okay? So then we could break it down this way. It's exactly the same expressions we used yesterday, except the difference is we're subtracting this time instead of adding. And so now we have something that can be reduced down. This will be pi over 3, and that will be pi over 4. So it looks very similar to what we did. It's just subtraction instead. And subtraction tends to be the harder one for students. But generally, if you have small angles or angles that are less than a nice angle in the unit circle, subtraction tends to work out well. And so that's kind of the basic strategy. And then once you have that, then you can rewrite this as the sine of pi over 3 minus pi over 4. Now you can use the sum and difference identity to calculate that out. And so let me emphasize here. Let's see, let's make this one green and this one yellow. So those are my two angles. And so the green part, I know that I'll have the sine, and you can look at the sum and difference identity if you want on your study sheet that I posted for you guys, or anywhere that they have it posted online. But it's going to be the sine of the first angle, and then the cosine of the second angle, well, you likely will get them memorized just from use, but not that that's necessarily the expectation. And then you're going to reverse that. So now it's going to be sine of the second angle. And so it's just flipped around is what it is. And sometimes they write it sine, cosine, and sometimes they keep the pattern the same and write this cosine sine. It really doesn't matter how you organize these, as long as the angles are different. So you have the cosine of one angle, and it's the second angle. Here, it's the cosine of the first angle. That order does matter. Okay, so sine, cosine, and cosine, sine. Basically, if I wanted to write this the other way, I could have written it like this so that the angles stayed in order. Okay, and different books write the identity differently. So some of them will keep the angles in the same order and just switch the sines and cosines. Some will keep the sines and cosines in the same order and just switch the angles, and it really doesn't matter as long as that's what's happening. And then now we can actually evaluate this. And I'm going to save this one for later since you guys had questions on double-angle identities today. But once you have all of this, you can go to the unit circle and you can find out, okay, what is sine of pi over 3? What is cosine of pi over 3? What is cosine of pi over 4? What is sine of pi over 4? Subtract those, and then you'd have an answer once you simplify. The big idea here, though, was I wanted to make sure that you guys understood that we're not limited to addition. Some angles that you're given work best with subtraction. You guys asked about double-angle identities, and double-angle identities are actually a little bit harder, but not because they're actually harder, but because there's more of them. So double-angle identities. Sine is actually really nice. Sine of 2 times an angle is just 2 times the sine of the angle times the cosine of the angle. It's the easy one, but it's actually not hard to prove. So if I wanted to prove it, sine of 2a is really sine of alpha plus alpha. And now I can use the sum and difference identities, which says sine of the first angle, cosine of the second angle, plus, because that's plus, cosine of the first angle, sine of the second angle. But just like I did in the last problem, the order of these can be, they're commutative, so I could just reverse these. So I really have sine alpha, cosine alpha, and another sine alpha, cosine alpha, which means I have 2 of them. And so this is sine of 2 alpha, and so that is the identity. Think of this as like smiley face, and think of this as smiley face because it's exactly the same. How many smiley faces do you have? 2 smiley faces, so 2 smiley faces. Well, cosine's very different because it doesn't have this situation in the same way. Now, I can actually do the same thing with cosine of 2 alpha, 2 alpha, by breaking it apart as cosine of alpha plus alpha, which if I go to the sum and difference identity would be cosine of alpha times cosine of alpha minus, because remember cosine has the opposite operator, and then sine of alpha, sine of alpha. So this one ends up looking very different. Cosine squared of alpha, cosine times cosine, minus cosine squared, sine squared of alpha. So that's one of the forms. But if you guys remember, the Pythagorean identity says that sine squared of something plus cosine squared of something is always equal to 1, which means I can replace, if I rearrange this, sine squared of x is equal to 1 minus cosine squared of x, or I could subtract sine over, and cosine squared of x could equal 1 minus sine squared of x. So I can replace cosine squared with 1 minus sine squared. So I could take this piece right here and replace it with 1 minus sine squared of alpha minus sine squared of alpha. And that gives me 1, and then there's 2 of these subtracted, so 1 minus 2 sine squared of alpha. Or I could replace this piece with 1 minus cosine squared. So I'd still have the cosine squared then. I'd subtract, and I have to distribute the negative into this because all of this is subtracted. So I'd subtract the 1, and subtracting a negative cosine squared would be a plus cosine squared. which gives me 2 cosine squareds minus 1. So this is one of the forms, this is one of the forms, and this is one of the forms. So cosine has 3 possible ways of writing it. And you just use whichever one's easiest for what problem you're working on. The double angle identities, a summary of them, we just actually proved what they were. For sine of 2 times alpha, it's always going to be 2 sine of alpha, cosine of alpha. For cosine of 2 alpha, you have 3 possibilities. Just use whichever one works. Generally, this is not the best one to use because oftentimes you don't know both the cosine and the sine. You only are given one of them. And so then you would use, if you were given sine, you'd use the 1 minus 2 sine squared of alpha. And if you're given cosine, you'd use the 2 cosine squared of alpha minus 1. So those are the double angle identities for sine and cosine. You can actually find the double angle identity for tangent very quickly by just taking sine of 2 alpha and dividing it by cosine of 2 alpha. All right, so let's say that we know this. What would be a situation where using one of these would be easier than using this? Well, let's suppose I said find cosine of 2 theta if cosine of theta is 1/7. Oops. And this is one of those cases where you can't find an exact angle for theta because it'll always be an approximation. Your calculator will give you this non-terminating decimal for theta. So there will always be error unless you use an identity. However, I have identities that allow me to rewrite cosine of 2 theta. And based on this one, which of the identities should I use? Yes, so use 2 cosine squared of theta minus 1 because you already know cosine of theta. You actually can find sine of theta if you know which quadrant the angle is in, but we don't know that, okay? But it actually doesn't matter because if you go to the identity, you'll always get the same answer because sine is squared in the other identity. So you could find sine of theta using a right triangle and then use the first one. It's just way faster to use this one. Any of the 3 identities always works. It's just one of them is usually the faster one to use. In this case, this one's fastest because I have cosine. But I need to remember that what this means is 2 times something squared minus 1. That's what this actually means. And it means the cosine of theta squared. And what is the cosine of theta? It's 1/7. And so then I can calculate this out. 1 squared is 1. 7 squared is 49. I see that I have a denominator of 49, so I'm instantly going to write this minus 1 as 49 over 49. Oops, that's not a 49. 49. Okay. And then I have 2 over 49 minus 49 over 49, which is going to be negative. Negative 47 over 49. And so that right there, even though I never found out what theta was, it didn't matter. So as long as I knew what the original angle was, I could find the cosine of twice that angle with only that information. And that's the power of the double-angle identities. They allow us to solve problems that normally would take us a lot of work to do.